week, I thanked a lot of people, and I said how we try to, always do something different. Sometimes we lose things, and one of the things that we lost in November was one of our volunteers, Bob Schnero. And I don't know how many of you know him. You will probably recognize him more when you see photos if you didn't know him personally. But he was a member of our Friends program. It used to be called our Associates programs. Many of you are members. He was one of our original volunteers for about 25 years. And that was Bob. And for many years, he just preferred to be the greeter. Somebody who would just say, "Hi, how are you? Welcome to Harbor Branch. Enjoy the show." And he took our tickets and things like that. He always had a lot of good stories. He was a high school football star, a high school coach. He was a teacher. He was a musician. He sang in the barbershop quartet locally. He had a lot of interesting things that he did, but he really enjoyed volunteering here at Harbor Branch. And here's some of the other volunteers. Some of them, his wife Pat was here volunteering still at the 4 o'clock edition. And you probably recognize some of our other regular volunteers, and I mentioned some of these. You also see Jill's in that picture. So Jill is behind the screen, but Jill was at that lunch a few years ago. So I just wanted to really thank Bob and also Pat for their many years of hard work, and a lot that's been in support of the lecture series. So thank you, Bob and Pat. I want to give a quick overview of the Indian River Lagoon, followed by a quick overview of water quality, and also some discussion of how we affect water quality in the lagoon. Talk about a program called the LOBO, or the Indian River Lagoon Observatory. Talk about something called LOBOs, or Land Ocean Biogeochemical Observatories. And many of you know a lot about the lagoon. It's something that I've talked about a lot in the series. We have a lot of other speakers this year, for example, talking on the lagoon. But a little refresher is never a bad thing. The lagoon is strategically located along the central coast of Florida. It's about 40% of the coast. The northern limits of what we call the Indian River Lagoon system is Ponce de Leon Inlet, which is north of Mosquito Lagoon, which is that part of the lagoon system that's north of the Cape, right along the Atlantic Ocean. And it goes as far south as Jupiter, so Jupiter Inlet. So we're kind of in the south central part of the lagoon where we are today. It is one of the longest systems like this in the continental United States. A lot of times you'll hear it's the most biodiverse estuary, or it's one of the most biodiverse estuaries. And you may have heard some presentations here by Paul Hargraves, one of our faculty members, who also argues that we don't really know enough to make that claim, that we need a lot more work on biodiversity here in other estuaries, and I would agree with that. Water quality over the last 80 to 100 years has changed very significantly. It's changed because we've altered the land and converted it to other uses, and how we drain the land and what we do on land. It's worth almost $4 billion a year to Florida's economy. A lot of that is recreational fishing. I'm sure some of you are recreational fishers. But also just ecotourism, boating, things like that. Mostly it's recreational value. Since the early 1990s, the agencies in the lagoon, which are mostly the water management districts and other agencies throughout Florida, decided that to really manage the system best, one should manage seagrass. And that's because the way I used to sell this for many years, being a plant person, not a lot of people appreciate seagrasses so much, is to understand the relationship of healthy seagrass with healthy fish and invertebrate communities. And so everybody cares about fish, right? Seafood. So healthy seagrass equals more fish. And also, I think the realization that one could connect improvements in water quality with improvement in seagrass habitat. And you've heard some other talks that I've given on that topic. And you all know, especially with the last year, some of the many issues that face the lagoon. I'm not going to go through each one of these. Freshwater releases to the south was a big deal in the last year. It's not the first time that's happened. That's something that's very predictable. I'll go out on a limb and say anytime it rains really quite a lot in Florida, in the center part of the state, in the south part of the state like it did this past year, those are the years we discharge from Lake Okeechobee. They don't really have any other choices. The water has to go somewhere. And currently it's plumbed to go mostly east and west. It was not the worst discharge we've had from Lake Okeechobee. There have been worse, and it happens every 4 or 5 years. But I'm going to mention some other events that were unusual in the last couple of years that haven't really happened before. And I find those to be the ones of greatest concern to me personally. So sometimes you read in the newspaper water quality, or sometimes people ask me, how's the water quality? And being a biologist, my answer always starts with, well, it all depends. And it depends on where you are, when you're there, and it depends on what you mean by water quality. So let me address the fact that water quality is more than one thing, and let me also then go through some examples and show you that it does matter where you are and when you're at a place about water quality. So the fountain of all knowledge, as you know, is the internet, and I went to Wikipedia for this definition. Heavily peer-reviewed, I'm sure, but I think it summarizes it pretty well. Water quality is the physical, chemical, and biological characteristics of water. So it's not just chemical, it's not just physical. I like to stress the fact that it has biology in there as well. That's an important thing to consider at times. It is most frequently used by reference to a set of standards against which compliance can be assessed. So a couple of key things there is there are standards, there are criteria when you do water quality. And there are certain issues of compliance. And there's kind of almost a legal aspect to that when you start talking about water quality. The most common standards used to assess water quality relate to drinking water, which we all know about. Safety of human contact, is it okay to swim in it? Is it okay to eat the fish? That kind of stuff. And for the health of ecosystems. What I mostly work on is the last point, ecosystems, and most of my colleagues here at Harbor Branch tend to work more on that area than the others as well. But there's a lot of other people who do work more on the public health side. So I mentioned there's physical types. Let me give you some examples. These are things like temperature and salinity, suspended solids, turbidity. I'm going to talk about these in detail in a few minutes. Examples of chemical parameters for water quality are things like dissolved oxygen, pH, that's how acid the water is, nitrogen, phosphorus, pesticides is a question that people ask about a lot. And also the biological, some things that you hear about a lot is bacteria. Are there too many fecal coliforms? Are there flesh-eating bacteria was in the news this last year. Chlorophylla is one that I'm more closely associated with because chlorophylla is a pigment that algae have that we'll talk about. That basically translates into algal blooms. So very quickly, I'm going to try to give you an overview of each of these. Let's talk about temperature because I think temperature is very important for organisms and also very simple. We all know what temperature is, right? It's how hot, how cold it is. And the hotter something is, the more the molecules move around. And that's one of the reasons why at higher temperatures things happen faster. The metabolism increases. And I can give you lots of examples of that. I'm going to give you an example for just a general relationship. In this case, I'm going to take fish. And this is just a cartoon from one of the textbooks that we use in one of the classes here. And you can look at the distribution of fishes from low temperature to high temperature. And you'll find for many parameters there's this broad optimum range where the fish are plentiful and they're happy. If you go too low or too high, the first thing that happens is they get stressed. Their metabolism slows down, their movements slow down, maybe their feeding rate slows down. If it gets too hot or too cold, we call that zone of intolerance. Another way to say that would be death. That's very intolerant of the environment. So you can think about this, and you can think back a couple years ago when we had two really cold spells in the wintertime, and we had massive cold kills, bigger cold kills than we had in probably 50 years. And that was a very significant factor because what happened is some of these tropical fish got stuck over here. There's a lot of other parameters that had that kind of relationship where there's an optimum, but too much and too little is a bad thing. Let's look at some old data I have, and just to reference this, it's always north to south when I show you the data over there. And this is a study I did a few years ago, and I worked for the Banana River where the space shuttles go off at the time, down to Linkport or Harbor Branch. And like, for example, I had some stations around Sebastian, some in Melbourne, some in Vero Beach. So a combination of stations that were in more urban areas and some that were in less urban areas. And so my shocking conclusion, and I hope I don't lose you on this one, is it is warmer in the summer than it is in the winter. See what science can do? Okay, but having said that, this was not an exceptionally cold year, for example. It didn't show those unusual events. And that's one of the reasons why you have to do a lot of long-term monitoring. I also did means of this just to show you that it does matter where you are in the lagoon. It is colder in the northern part of the lagoon by about 2 or 3 degrees centigrade, which is 5 or 6 degrees Fahrenheit or so. The average temperature is about 26 degrees Celsius or centigrade. That's pretty warm. That's about 79 degrees Fahrenheit. Some of you come from places up north where the estuaries never get to be that temperature in the summer. Okay, so we have a very nice condition for plant and animal life. So salinity, you all know what salinity is. It's how salty something is. We can get technical and say it's the amount in grams that's dissolved in a kilogram of seawater. That's how we've defined it for years. People throughout the world at one time or another have evaporated salt water to get salt because it's an important commodity. You know, it was once more valuable than most other things. It was used as money in ancient times. And historically, that's how we would evaporate water and get it that way. But there's so many new techniques now for doing that that we have much better instrumentation, which I'll talk about. This is just another cartoon from that same textbook, which basically shows you that it matters what the salinity is in terms of how many organisms or how biodiverse is in the system. So for example, you'll see this highest line here. It goes all the way up to the top. That's the distribution of marine species. And there's very few that make it very far all the way into the estuary. Most of them are most successful outside the estuary. The average salinity of the ocean nearby, for example, is 36. And then there are some, we call them euryhaline, that can handle broad temperature tolerances or salinity tolerances in this case. And they're found fairly far into the estuary. There's very few freshwater species that can live in salt water. It's very difficult for most organisms to live in salt water if they're not adapted to it. There's also a very few numbers of species that are true brackish water species that actually prefer low salinities. That's probably the harshest place to live in the environment. So when you have really low salinities in areas that typically have higher salinities, you can see why that's a very stressful thing overall for plants and animals. Here's some of that data from that old study I did. And forgetting about the magnitude of data, you can just see there's certain parts of the lagoon where salinity didn't vary very much week to week. Those are our 2 years of weekly data points. And that's true in the northern part of the lagoon. And Ned Smith, who was here at the 4 o'clock lecture as a physical oceanographer who long ago showed that the residence time in the northern part of the lagoon is about a year. It takes a drop of water about a year to go out an inlet from there. Whereas down where we are, Vero Beach in Harbor Branch, it takes about 3 to 5 days for that exchange to happen. In places like around the inlet, like Sebastian, you can see we have the most amount of salinity variability because we're getting a lot of freshwater inputs from one aspect, the Sebastian River, and we're also getting flow of salt water in from the inlet. So it's colliding and mixing. So actually, that's the most variable location. So it really does matter where you are in the lagoon. And this takes an average of those numbers. This was a period of time when it was a little wetter than it's been in the last 10 years or so. So the salinities are a little lower than what we've seen. And around Melbourne, we were having salinities as low as 15, which from that previous graph, you know that's kind of getting stressful, pretty stressful. You can see at Harbor Branch, the salinity was about 27. The long-term average here at Harbor Branch is 28 parts per thousand, so it wasn't that far off. Another parameter on that list was dissolved oxygen. And again, you all know what oxygen is. Dissolved oxygen is just the amount of oxygen that's dissolved in a body of water. And to give you some perspective, the range that we see in marine waters is from 0, which means no oxygen, which means dead zone, anaerobic, to 13. 13 is pretty high, okay, and it would happen also at low temperatures. Because the lower the temperature, the more gas a fluid can hold. Also, the lower the salinity, the more gas it can hold. So how much oxygen you have in the water depends on physical conditions like the two I mentioned, but also it depends on biological production. Photosynthesis produces oxygen. Plants do that. Algae do that. Respiration occurs by all organisms, so plants, animals, microbes. So it's that balance between the two of them. And this is just a chart from the Long Island Sound program, another estuary. Usually 5 milligrams per liter. People don't have any concerns, or the organisms don't really have any concerns. Concerns start to happen when you get down to 4 parts per million or 4 milligrams per liter. Some organisms are more sensitive they'll undergo stress. If they can migrate, if they're mobile, they will. If they can't, they're stuck there. If you get down to lower oxygen levels, like around 2, you start to have mortality. And by 0, it's essentially everything that requires oxygen would die fairly fast. So sometimes fish can get away. Sometimes they don't. A lot of times we have fish kills in the summertime when the temperature is high and there may not be much water movement. There may be a lot of decomposition going on, a lot of microbial activity. And if the fish can get out, they will. But think about a sponge that doesn't move around. If its oxygen levels stay too low too long, there will be sponge mortality. The data I have for oxygen, I don't really have something for the lagoon that was very handy. So I looked at some old data I had from St. Lucie estuary. For those of you who don't know the St. Lucie estuary in Stewart, you know there's a North Fork and the South Fork that are heavily influenced by freshwater runoff. Part of that's from Lake Okeechobee, part of that's from the local watershed. And south of the Roosevelt Bridge, which is the Route 1 bridge, we have the area that's called the mid-estuary, and then the lower estuary is very close to the Indian River Lagoon, and then a lot of this water flows out the inlet. And basically, if you look at like what is at the lower estuary for this particular year, you can see it was all above 5. It was all pretty good. It was also, you see, it doesn't vary much from year to year. I mean, from month to month. That's a good thing. But you can also see places like the North Fork and some of the other sites where we were getting below 4 for sustained periods of time. So even in this particular year, which was not a particularly bad year for water quality, there probably was some localized stresses in the system. I've shown this in other talks, basically to introduce the idea that I'm really a plant person. I'm interested in seagrasses, as I mentioned earlier. And seagrasses have a high light requirement. I've talked about that at length in the past as to why. But for now, let's just accept that that's true. And some of the things that really reduce light are suspended solids and color and chlorophyll. And I did that report that I mentioned a while back. That's what it looks like. If you really want to read the whole thing, it's 505 pages. Be glad to hook you up. There's no Reader's Digest version, I'm sorry. But I did a lot of statistics. Like the question was really, what influences light availability of seagrass beds at those 6 locations? And overwhelmingly, the #1 factor at that point in time in the lagoon was turbidity. That's the particles in the water, followed by water color, and followed by chlorophyll A. So let's take a look at those 3 parameters. First one is turbidity. Well, I think most of you know what turbidity means. Turbidity is basically the cloudiness of a fluid. And these are not the big particles. These are mostly a lot of little particles, microscopic. These are ones that we can filter out onto a filter, a very fine filter. We can weigh it and get an idea. We can quantify how much that is. But visually, this beaker has very low turbidity. It's very clear water. And you can see as it gets increasingly cloudy, the turbidity numbers would go up. And we can quantify these in different ways. And this one goes the other direction. So low's over here, high's there. And this is something called nephelometric turbidity units, or NTUs. We use that elsewhere in the presentation, NTUs. In the lagoon locally, most of the time, we have low turbidity, 10 or less. Some of these other issues happen in other types of systems, or, for example, if you had a really bad outfall drainage situation where, for some reason, you were doing really bad construction purpose, doing some dredging or something, and you could get quite elevated turbidity. So it's usually just a local phenomenon to see anything higher than about 10. Color, or if you want the fancy name, chromophoric dissolved organic matter, or CDOM for short, is something that we can measure optically that relates to the amount of dissolved organic material in the water. And that organic matter has color to it. And this is a schematic from another organization on the other side of Florida, which basically just kind of shows you like turbidity. You can have very low color, and you can measure it and quantify it. The more color you have, the higher the number you have. And the best example of this locally, very conveniently nearby, is Taylor Creek down in Fort Pierce. And you can see the greatly discolored water that's associated with the freshwater discharges of that site. You go to Vero and see it there. You can go to Martin County and see it. a student in one of my classes a few years ago. I had this picture from her of a field trip that we did down there, because I use that as a local place to go to show students water quality gradients between here and the lagoon. This is basically the result of natural decomposition of terrestrial or aquatic vegetation. And mostly it's tannins. So not unlike tea. Think about tea. Same kind of discoloration, decolored water. And it's not really toxic. Sometimes people look at this and they say, oh, that's algae, or oh, that's dirty stuff. It's colored water. And it does, like I said, it's a major attenuator of seagrass, so it's something to be concerned about. But it's oftentimes misunderstood. Chlorophyll A is found in all plants, and we use this as an indicator of the microscopic algae or phytoplankton that's in the water. These can include things like cyanobacteria or blue-green algae. And I see Nicholas in the room. He gave a talk on some of these last summer. And some of them are toxic, and some of them aren't. They fix nitrogen, which is kind of interesting. Diatoms, which are a major ecological grouping. Very few of them are toxic. There are a couple that are. And the last one is a picture of a dinoflagellate, which causes Florida red tide, which this group has a lot of toxic organisms in. And so when you're measuring chlorophyll A, you're not saying what type of alga. You're just saying collectively, this is the amount of algae that you have. And like I mentioned, this is the same pigment that is found in all plants. So your lawn, citrus, mangroves, palmettos, all of them have the same basic apparatus underneath things. So I mentioned that what was really unusual that concerns me is what happened in 2011, where we had something that now has been called the 2011 superblue, which had an unprecedented amount of chlorophyll A and cells of this particular organism, which is called Rosaltor, which is a tiny green flagellate. That's an electron micrograph of it. So it's very, very tiny. And it was in the Northern Lagoon in April 2011. And it was the highest level of chlorophyll for the longest period of time that's ever been recorded by anybody in the lagoon. And that began a series of seagrass declines. About 45% of the seagrass was lost right away, which is quite a lot. And the following year, we had a brown tide, which is caused by a different organism, a different flagellate. Both of these cells, both of these organisms had never been seen before in the lagoon. And all of a sudden, we have major blooms back-to-back years. We know more about this one ecologically, and what we know is not good. It was problematic in several of the northern estuaries, but most notably in the 1990s, for almost a decade, it bloomed and had serious impacts on the resources, including seagrasses of the estuaries. And that system is very like ours. And the beginning of that bloom is a lot like were the conditions when our bloom started in 2012. Let's talk a little bit about nutrients, or some people like to say fertilizer. Nitrate is the most abundant form of inorganic nitrogen. There's other forms, and it's essential to the growth of plants and animals. But like I mentioned for some things before, if you have too little, the plants are limited in their growth. If you have too much, you can get too much growth, and you can get a lot of these problems that we talk about with eutrophication, which we'll get into. One of my favorite macroalgae is Gracilaria. It's the most dominant macroalga in the inner lagoon. A number of years ago, I did a fairly simple study where I basically looked at the amount of internal nitrogen in the plant and looked at the growth rate. This is growth up here. And when I added more nutrients, as growth was going down, and I just gave them a little pulse of nutrients like you could do with any nutrient source. So it could be, fertilizer, it could be septic, whatever. Got a very rapid increase in nitrogen content of the plant and a very rapid increase in growth. And this just goes to show you how dynamic and explosive some of these organisms can be. And it's not uncommon to see large accumulations of these drift macroalgal populations dominated by Gracilaria. In the last year or so, there's been a lot of discussion about the changes that have happened in the lagoon. And that will be talked about in some additional upcoming lectures. The other major inorganic nutrient is phosphorus, and in particular, the inorganic form is phosphate. Phosphorus is a little simpler than nitrogen. There's really only one inorganic form to worry about. This is just a graph that shows the fact that all these nutrients cycle, And what we've basically done is, with some of our practices on land, is that we have added a lot more nutrients that get into the water system. And basically, as was discussed in last week's lecture, basically all of the freshwater areas lead into the estuaries lead to the coast. So it leads to marine eutrophication. So one example is, what farmers do in Iowa and Ohio, it ties into the dead zone of the Gulf of Mexico. Okay, so that was something that was shown last week. I drove across the state the other day, and as I was thinking about this talk, I said I should mention this because I was driving through the phosphorus mining area of Florida. A lot of people don't even know about this, but a lot of people ask me, what about this thing with fertilizer and phosphorus? What's the big deal about phosphorus? Do we really have that much phosphorus in our soils? And we do. Florida has a lot of phosphorus in its sediments, and in those particular 4 counties, that is the second largest source of all phosphorus that's mined in the world. And a lot of people don't know that. And a lot of people don't realize that this is deposits that happened when we were submerged. I wasn't here. Maybe some of, nobody was here. I wasn't here. But 10 million years ago, when we were submerged, a lot of these deposits were formed by organisms that were decomposing and accumulating these deposits. And this is what some of that mining operation is like, and you can drive across Route 60 if you want and just go right through it. So the overall model that I've used for some time and that other people use is what we do on land impacts the loadings that we put into water, which impacts water quality. So our activities on land impact what goes on in the lagoon. In particular, I like to focus on light and seagrasses because that's what I do, and because of the relationship of seagrass and overall ecosystem biodiversity and productivity. And so in my work, for example, we see highly variable seagrass abundance and presence based on where you are. And I talked about this in other lectures, that's heavily tied to water quality. So some species like Thalassia or turtlegrass have a much narrower tolerance for certain types of extremes like salinity, whereas haliduli or shoalgrass is found all throughout the lagoon and is much more tolerant of certain things like salinity changes. But as we saw in the die-off of 2011 and 2012, and most of what was lost was haliduli to the north, it cannot handle extreme long periods of low light. Also, areas that have better water quality have greater diversity of seagrasses. So you'll see a lot of the other species that you don't always see, such as the halophilas, the little tiny seagrasses. And there are cases where when water quality has declined, seagrasses have been lost. If you improve water quality, seagrasses will return. A good case of this is manatee grass or Serengeti in that same area, Banana River that I looked at. That station and some other areas up there had a big die-off in the 90s. And it took 5 years to 7 years for the seagrass to recover. Okay, so we think about recovery for what's going on now, realize it's not going to happen in a year or two. So how do we impact Indian River Lagoon water quality? And this is a little cartoon I found. It basically shows you all the different things one should consider. So of course there's agriculture. There's also atmospheric inputs. There's septic tanks. And Brian LaPointe's here. Brian in 3 weeks is going to be giving a talk on the whole septic tank issue. I'm sure you've seen a lot of the news in the paper about Brian's work on septic and some other work on nutrients. So you're going to get quite a lecture that night from Brian. A lot of this comes from the fact that we have a lot of impervious surfaces. We have all these huge parking lots. So anything that we leave out there, like things that drip from our cars, you see that all the time, right? When we get a rain, it all comes down, goes in the canals. Fortunately, we don't have a lot of industrial waste, but this just gives you some of the different things to consider. And everybody wants to know which one is it, and I for one will say there's a lot of them, and we need to think about addressing all of them. The biggest challenge now is all these non-point sources, the days of just a single sewage outfall. Most of that doesn't happen anymore in the lagoon. The only time it happens is with overflow situations. It's very limited for sewage systems, not for septic. And runoff at any point is based on the land use, how much rain you get, characteristics of the soil, is it sandy, percolates well, or is it clay and doesn't percolate well? So if you have different types of uses, and these are categories that people use a lot of times, and you have rain, the amount of loading that's expected, and this example is suspended solids. So industry, in this case, has the biggest impact, followed by agricultural, followed by housing, and much farther behind is open range land and recreation areas. And again, this is just ballpark numbers. And a lot of times that's all people have. They use the best available data. So everybody's residential area is not going to give the same number. That's just an average number. If we look at time from 1920, when everything was pretty much undeveloped, and this color here is all natural, and you can see just a tiny little bit of agriculture, and you see a little budding Vero Beach here. Melbourne doesn't look very big yet. And as time goes on, you can see more agriculture. So by 1973, we've got quite a lot of agriculture. But you see at that point, the cities, Vero Beach, Melbourne, Cocoa, have really started to become more significant. And as time goes on, you can actually see that agricultural withdrawals or get smaller. In urban areas, really expand. You can see enormous development here, for example, in Brevard County. So this is really interesting. So you can see that land use has really changed, and you can see the direction is away from natural environments where there's very low natural loadings to those that have much higher loadings. So for example, this is how one location looked in 1943. Now I know Brian knows where this is, but can anybody else say where that is? What other community had a golf course before it had bridges to get to it? Yes, Vero Beach. Okay. And, but that's just to show you kind of the impact that happened in less than 5 decades, 50 years. So, of course, the main ingredient in all this is the fact that we discharge a lot of water that used to flow historically down the center of the state. And there's been a number of talks. Mark Perry gave a great talk in October about this. And we have all the canals, and they are very straight, and they're meant to discharge water very, very fast. And they do a very good job at it. That's what they were designed to do. Here's some of the locks coming from Lake Okeechobee. I'm sure some of you have seen these types of signage in our local area, reminding us that all canals lead to the lagoons. And it goes in the canal, it's eventually going to end up in the lagoon. So some of the areas of good water quality historically was the northern part of the lagoon, especially around the Space Center, Merritt Island. That was kind of an unplanned, protected zone. It was protected for security, but it became a wildlife refuge. It's kind of cool. The shorelines up there, there's some very spectacular shorelines, really a lot of natural shoreline. Very good place to go. There's many good mangrove areas around here. And mangroves are real important, you know, for filtering some of the things that come off of land in a natural setting. And we also know that inlets in general, because of the flushing, because of the oceanic water, tend to be hotspots of biodiversity. And areas that we know about that have bad water quality, that's that same chart of Vero, but not to pick on Vero, but urbanization in general has been detrimental to water quality. The St. Lucie estuary that I mentioned earlier to the south, you all know what happened with Lake Okeechobee discharges this past year. And those plumes of fresh water you can see going out into the inner lagoon, then out the St. Lucie inlet, and they flow, in most cases, south, where there's an interesting coral reef system. And in 2 weeks, we're going to have a lecture by Dr. Joshua Voss and Jeff Beal from the FWC that will discuss that particular system and that particular issue. So I hope you can come and enjoy that talk as well. So what we know about changing in water quality through time is that we actually have limited historical data. Our good data doesn't go back that far. It goes back to the 80s. There are some isolated things in the 70s, but we don't really have as much data as we would like long term. And we've seen enormous changes during that time with the biology and with our living style. There's lots of interannual variability from the data we have. Overall, the trend is down. Here's a report that was done in 2007, which I think it was a review of 10 years of changes in the estuaries. And the thing that was identified then, which is already now 7 years ago, was an expectation that we'd have a large increase in both atmospheric and urban nitrogen load predicted as a result of expected population increases. So that was forecasting the future. Each estuary has a little page. You can look this up. You can look at the indicators it has. Overall, it's kind of got the moderate box, which I think some people in the room might take an issue with. But in the end, a summary comment was, in general, the overall eutrophic condition of the Indian River has been characterized as moderate and remains unchanged since the last survey. So they didn't think there'd been much change in 10 years. And, but there was change from place to place. So some areas that have not changed. This was pre-bloom. So the Banana River and Mosquito Lagoon haven't changed very much at that time. Other areas have improved, like the northern IRL, and others, like the St. Louis Estuary, have worsened. It would be really interesting to see what this report's going to look like in the next update based on the last couple of years. So who's responsible? Well, you've heard me kind of summarize this already. It's a lot of different sources. It's agriculture. It's what we do in our yards, and you've seen a lot about that in the newspapers. It's the historic digging of canals, which were initially done for transportation and rapid movement of water to get it off our land so people could build houses, so people could grow crops, and so on. And we've talked about the freshwater discharges, which impact things not just in the local estuaries, but offshore as well. And we know there's some impact from boating practices. And maybe some of you remember other talks where I've mentioned Pogo and his famous line, "We have met the enemy and he is us." I'm sure some of you remember that. If you want to know more about Pogo, you just Google first Earth Day, because that's when this came out, and Pogo. And you can learn all about Pogo and Earth Day. And that was really quite an event, Earth Day was. Kind of lost its power over the years. So I want to talk a little bit about the Indian River Lagoon Observatory. And our efforts at Harbor Branch the last 2 years is to really take a long-term, multidisciplinary, ecosystem-based approach to better understand the environmental health of the lagoon, to better understand how it functions, to better understand its biodiversity, and how all this is impacted by the surrounding population, so all of us. So our goal is to acquire and disseminate data and knowledge on components of the IRL critical to its ecological function, how it works, and sustainable management. In other words, can we keep it in good shape in perpetuity? So key elements of this, and a lot of other speakers, myself and others in the past and in the future, have or will talk about some of our long-term multidisciplinary work. We have a lot of collaborations with other organizations, and we can give you some examples of that later. But what I really want to focus is the third element, which is a network of advanced observing stations. And in particular, this is LOBO, Land Ocean Biogeochemical Observatories. And this is something that Harbor Branch decided to make an investment a little bit more than a year ago. And this is really what I want to leave as my major take-home story for you today. Our overall goal was to develop a estuarine observation network that would provide real-time data so we can get it right away. And it's highly accurate. It has high-resolution water quality data. And like I said, we can get it right away through a dedicated interactive website. And I'm going to show you that. We measure these things. I've already told you what they are. I told you why they're important to measure. So I'm going to assume that you now know all that. And we have a website. This is a picture of that, and I'm going to test it for real. Now, a big part of this, and some of the other folks were here, Brian's here tonight. So Brian and I have a great group of people that work with us. And I'm sure he would agree with me that the folks up here have done an incredible job on this and other work. And I'm going to show you some images later and try to address that. But it really takes a lot of different types of talents to make a system like this work. This is a picture of Google Earth. So our Lobo site, our main site right now, is right off of Harbor Branch. You're sitting right here. You can probably see yourself if you look carefully. And we work right out in the Indian River Lagoon, right at the end of our channel. Why? Well, it is convenient. But more importantly, that's right next to that link port station that I showed you some old data for. And this area is probably the most studied site scientifically anywhere in the lagoon. So it makes a lot of sense to do that, both looking back through time, but also looking into the future. Here's what a Lobo looks like when it's brand new and everything is nice. Has that new car smell to it. The brain of the system is Storex. okay? And it's basically a data logger. It's a computer that gets all the information from all the other sensors. And it keeps it, and every hour it sends a signal up a cable, and it's transmitted basically by email, you could say, wirelessly, to a server that then makes it available to all of us. We have something called the WQMX, which part of it is a traditional like CTD, which measures temperature, depth, salinity, oxygen. But the part that I really appreciate the most is the other end of it, where there's 3 optical sensors here. And these measure the attenuators of light that I'm very interested in, being a plant person. So that's where we measure turbidity, chlorophylla, and watercolor, or CDOM. But it gets better, because for years, and I'm sure Brian started this way, I don't know if he did manual chemistry when he was a young lad. I did. And after a while, we said, we'll send them to a lab, and that's all they do 24/7, and we do it that way. But that takes weeks sometimes to get the data. So here we have an optical sensor that gets us nitrate real time. We ask for it once an hour. We could get it more frequently with that device if we wanted it. And then lastly, another nutrient is phosphorus, phosphate. This is done actually chemically. I call that chemistry in a can, that particular part of the system. And it really does have a miniaturized chemistry with little tubes and a little spectrophotometer type device. So the first thing you do is you totally cloak this with tape and anti-fouling paints, because fouling is the biggest single problem. And we also have to only send it back without any paint on it, right? I mean, one of our vendors is here, so I gotta be careful. Or we violate the warranty. So it's very challenging. But then there's copper wrapped items. There's a lot of anti-fouling items that go into here. So this is all the different devices, just like I showed you before. And we also have something I didn't mention on this particular one called an aquadot, which measures current, speed, and direction. We also have at this site a weather station that measures light and temperature and rainfall and so on. It has solar power to it, and we have the transmitter of the information back to the server. And again, a very key part of this is getting that data real time. So now I want to show you what I'm going to call a quick look behind the scenes with Team Lobo. So that's what everything looks like when it comes in the nice boxes. We had a great group of people, and I want to recognize Daryl to the left. He was from Satlantic, so they sent somebody here for a week to get us going. And this is in our engineering building. You can see this is our very first time. We tested things to make sure everything worked in a special tank that was in the engineering building. You can see a lot of our team doing that. This is a quick flyover of our Lobo site. So basically one of the existing pieces of, what do you call those things? Moorings. There you go. There we are on our first day, and I think that's Jennifer, by the way. Jennifer's in the video. Jennifer Zimmerman is the person who sold us the material. So if you're interested, she can hook you up. That's our weather station. Everything's not connected to it yet. And so we're approaching this. We have a special boat that was sitting here. We modified for use, so we have a dedicated vessel. And one of the really cool things, Brian and I went over to see some other folks that have a system like this, and on the way back we were saying, we don't want to put divers in the water, because everybody else that works in estuaries puts divers in the water. But we have conditions like this, like we've had the last few weeks. And you really can't see. It's not really safe, and it's very challenging. And you can see the transmission of the signal goes back. This is Kristen. Kristen was here at the previous lecture. She actually looks at the data as it comes in every morning to see if there are any issues. So if we're not getting a signal, or if we're starting to see maybe some signs that sensors are straying, she can look at the data. She can print this out. I'll show you how that's done. But that's the real sound of 2 weeks ago. This is one of our newer employees, Billy Wells, and Ben Metzger. Ben was one of the folks that initially did a lot of the deployment and a lot of the engineering side of it. And he's transferring a lot of that skill to Billy. And Billy's going up. We have a very simple pulley system. and that weighs more than 100 pounds. And you can see that Ben, with the help of the pulley, can very easily handle that and secure it on the deck. And then that allows us to check out and test the calibration of a lot of the sensors, because one of the concerns is it's only as good as the drift of the instrument. So if we start to see fouling or some other types of problems, we need to identify that quickly. Sometimes we can see that remotely. We can see some strange numbers, but we also go out and download certain data files that aren't transmitted. What we're doing here is that's the Suna, and they're putting in distilled water inside so the optics can work as if it was underwater, and we basically check the calibration. If the calibration isn't quite right, they can adjust it right away on site. If it's a more serious problem, we can just take that component off, bring it back to the lab. We can work with it. We can call our vendor, the service technicians, and get some insights. So again, I want to emphasize the fact that we can do this anytime we want without having to go in the water. And more importantly, we're getting data regardless of what the environmental conditions are. So we're getting data when it's too rough for me to send somebody out, or too rough that I would go out and get in the water. If we have a hurricane or a tropical storm, our intent is to leave this out and get some incredible data on water quality. I sometimes think, I wish I had these in 2004 for those 2 nasty storms that we had. So you can see we give everything a bit of a cleaning. Periodically we'll bring the whole thing back to the lab and totally clean it, several times a year. But in most cases, that's how it is returned. It stops automatically 1 meter off the bottom, so it's kind of at a fixed depth. That was 2 weeks ago. Now last week we went out, and this is Kristen on the left, Laura on the right. Kristen works more for me. Laura works more for Brian, but we all work together on this. And they're going to take a bunch of grab samples, so the way we normally collect water quality, and they're going to analyze it either with instruments right away on site or very quickly back in the lab. So there's Laura taking one measurement, oxygen and temperature, and going to deploy another CTD that's going to measure several of those parameters very precisely. We do this exactly at the same time that sample is being taken by Lobo. So we match it up very precisely to the minute, okay? We also take some water samples. So this is called a Niskin bottle. And again, we drop it down to the same depth as the Lobo sensors are. That's a little messenger that triggers the collection of the sample. And you can see Billy bringing the Niskin bottle back up. And then from that, we can take several samples. We take samples for nitrogen and phosphorus. We take samples for dissolved oxygen. And you'll see, I think, Billy doing the dissolved oxygen probably first. And we actually do traditional chemical titration. And it starts in the field with addition of a couple of chemicals. And then Kristen finishes the work back in the lab the same morning. And Laura is taking nutrient samples. And those samples come back. And Brian in his lab has an autoanalyzer that basically will run the samples that day. So we will know literally within a couple hours of whether we had any issues at all with our units. You can see our very scientific appraisal that it was cold that day. And that's actually a little iPad. And one of the things Kristen did is she made a little application so that we can record all the data directly electronically. Don't have to come back and do it. Sometimes people get a little tired at the end of the field. This is at our small boat marina. Day is not done. They now have to take the samples back to the lab and do all that other analysis like I mentioned. So again, I really want to thank everybody that does this work. We couldn't do it without it being a group effort. And what I want to do now is hope that the internet works. And I just clicked on that link. And I actually have some handouts here. I did a little primer on this, or primer, whatever it is, in October after our first 4 months. So you can go use that link, or you can just Google Harbor Branch LOBO, and you can find the site very quickly. So this last reading was taken at 1900 Eastern Standard Time today. So that was 7 o'clock when the lecture started. The air temperature is down to 12.4. That's 54 degrees Fahrenheit. So we got it in both temperature units. We have, there's a few things that we do that way. It didn't rain today. I guess we knew that. The sun's basically gone. We don't have much light out there at all. Must be a little moonlight. The wind's gust over the last hour has been about 7 miles an hour. The average speed's been about 4. And then below water, the temperature is 16.2 degrees Celsius. It's about 61 Fahrenheit. Salinity is about 24. I told you historically the average here is 28. The dissolved oxygen is pretty high. It's 10. It's above 100% saturation. You'll see I like to use this saturation number a lot. Turbidity is fairly low. Color is probably medium. And chlorophyll is kind of in the average range, and so on. But what a lot of people don't really bother to look at is they don't see the fact that there's a lot more than just what's going on now. You can click LOBO Viz up here, and you see a screen that looks like this. And you can pick and choose what types of data you want to look at, and you can also save the data. You can put it into an Excel file or some kind of statistics package if you're so inclined to do that. So for example, let's take temperature, and I'm going to do it in Celsius now. And I'm going to get, I have all these choices of what dates I want. I'm just going to take all the dates. So our database that's out there for the public started last June. And you can see this is just like that. It pulls up all the data. And you can see, again, quite a surprise. It's hotter in the summer. So that's something you picked up early on, right? All right. But you can see some other things. You can see that the temperature, you know, once it gets hot, the water stays pretty much very similarly for most of the summer. You can see, as you have experienced, if you've been here since early November, you can see each of these drops. They're fairly sharp. And what we can do is we can say, you know, well, you also have weather data, right? What was the air temperature doing then? And we can go ahead then and we can plot that. And you can see these very sharp cold fronts come through here. You can see that in the summertime, the water is actually heated up in most cases more than the air temperature because of all that sustained insulation through time. And you can see it's more tightly related here, but you can see there's some big drops, and they're associated with these cold fronts. So as you can see, we're in the middle of another one tonight, right? We all know that. Maybe you are a fisherman, or maybe you just want to know, you know, what are the tides at Harbor Branch? So to do that, for example, we can go back here, and we can take depth, because depth is basically going to give us tides. Let's do feet this time, and we'll still do all dates initially. And when you do that, you can see, okay, as you know, high and low tide each day, so that's why it looks, you know, like there's a lot of ups and downs each day. But you can also see that long term, the tides, as you know, if you live all year round, are a lot higher in the fall, like in October and November, than they are earlier in the summer. Okay, and that's something that happens repeatedly every year. The details may vary a little bit, but to really tease out some things with tide, maybe we could take the last week instead. And we can plot those data. And now you can see more clearly that each day there's 2 high tides, 2 low tides. You can see that the high tides are unequal. Okay, some places of the world they're very equal, other places they're very unequal. These are very close to being equal, but they are not exactly equal. And then you might say, well, I'm interested in the salinity. How does salinity vary with tides? And what would you expect? High tide should be what? Higher salinity or lower salinity? Should be higher salinity. Let's see if it is. And we'll just do it again for the week. Okay, so now you can see the nice tide cycles here. And you can see salinity is not quite as sharp, but you can see very high correlation with it. You can see certain days it isn't as tight. When you look those up, those are days when we had heavy winds. And oftentimes if the wind is in the opposite direction, it's going to interfere with what you would expect to see a little bit. But if you look through time, this is pretty much true. We could look at all of the salinity data for since June, and this is what we see. I told you the average salinity at this site is about 28, so I'll draw the arrow across the average. You can see a lot of times where it's a lot higher. You can see we had this big depression, which was associated with the beginning of the wet season. You can see there's a very sharp onset of the wet season. And I think all of you were probably here a few days ago when we had this very heavy, atypical precipitation for January. And we see a very change in salinity here. Now, I told you earlier that color is a good sign of fresh water. So we could say, okay, is that true for this station? How does that look? So now this is salinity, and which is now they changed color on us because that's the way the program works. Depends on how many things you have. But you can see that salinity goes up, color goes down. Salinity goes down, color goes up. You can see a very high correlation. So again, that means, you know, when you're out there in nature, you see color, you know it's freshwater inputs. Yes, we can model this data for you. We can also, let me show you that we can also take like CDOM, and instead of going through time, we could say, what's the relationship of CTOM to salinity? And we should see some pattern. And not surprisingly, we do. And you can see, yes, sometimes we get outliers, and maybe that's a data point we might want to take a look at, see if there's any reason why we might want to eliminate it, but you see it's not going to change the overall pattern. There's a very strong relationship between CDOM and salinity, very sharp. And if we just want to see the oxygen record, I like to look at this percent saturation. And the way I like to look at this is that 100% saturation is basically telling you that the water is in equilibrium with the atmosphere at that salinity and that temperature. So when you have numbers that are above that, that means what? You have a lot more oxygen. Why is that? Because there's a lot more oxygen. Photosynthesis, right? Is the main reason. So when I look at this overall pattern, I mean, why it goes up and down so much, you'll see, is because it is not photosynthesis 24/7, is it? It's mostly during sun times, daylight. But you can see this great depression here of oxygen saturation. And you might recall a graph that I showed you earlier, but if you forgot, we can just go ahead and plot that. And we can plot salinity. And we can see that this period that I mentioned where we had very rapid decline in salinity, which means lots of freshwater discharges from the canals in Vero Beach, the 3 relief canals, you can see that's when we have the most serious depression of oxygen. So that, to me, says that freshwater inputs into the lagoon are, in fact, overall stressful for productivity of the organisms. You can also see that with this current situation where we have low salinity because of that unusual rain in the wintertime, we're not seeing that as an issue, okay? So the same freshwater discharge might have a different impact depending on what else is going on. Let me just wrap up with a few more comments. I know I've been running probably a little long. So I hope that we've convinced you that this technology will provide scientists, agency managers, people like that, students, whether they're university students or high school students, and just public like yourself, unprecedented access to Indian River Lagoon environmental data. I was really pleased to learn that the Water Management District, St. John's, have purchased equipment that's somewhat similar to this. I say it's got about 2/3 of the capability of the LOBOs, but it's the same technology. They're going to be deploying at 5 locations they've started. One of them is in Vero Beach on the 17th Street Bridge. I'm really pleased about that because they are instrumenting all the way up to the Mosquito Lagoon. We'll have access to that data, and it will definitely help us in some of our research to have that. So we're providing the real-time access. We're interested in following environmental changes in the IRL, but also to do comparative studies. So I mentioned Brian and I had gone to the other coast, to Sanibel Captiva, where they also have a network of LOBOs, and they receive discharges from Lake Okeechobee via the Caloosahatchee. So we've been writing proposals to try to instrument the St. Lucie estuary, and one of the things that it will allow us to do is also do comparative work between East Coast and West Coast discharges. So I think that would be a very cool thing to do. We hope that this will lead to better management decisions for the IRL. We plan to use a lot of this data in environmental models. We've hired, you may have seen a brief news article, we hired a couple of physicoceanographers. One of them has been involved with proposals with us already to try to take the data and model it and apply it both in a hindcasting, looking back in time, but also in a predictive way into the future. And we think it's a great way to teach students about the local environment and outreach. And again, you don't have to be here. You can do this from your laptop at home. One thing I don't think we've been talking enough about, but you'll probably be hearing a lot about in the coming years is restoration. All the seagrass losses, all those oyster reefs that were lost in the St. Lucie estuary. There's a lot of interest already. There's requests for funding to try to help restore them. And you must realize that water quality is a big part of what's needed to make successful restoration. Indeed, some of these projects, like planting more oysters in the lagoon, is actually an attempt to improve water quality. So you want to have monitoring that actually can support that. And we're really looking long-term with this for things like seagrass restoration, oyster restoration, fish restoration. And we think that strategically locating these instrumentations and tying it to restoration, tying it to management decisions, we can find out. People spent $100 million. Was it worth it? Did they deliver the goods? They said there was going to be this amount of improvement. Was there? That's important to do. So I think we can quantify all of these things very carefully. I didn't point out on the website, we have a very major effort at QA/QC. You saw it in the video, but you can read it on the website for those of you who are interested in the techniques. But then again, it all gets back to POGO and us. And the reality is that, as you saw in the local newspapers on Sunday, there already is a beginning of a new real estate boom market. Developments that were stopped in 2008 are starting again. And more people will always be coming to Florida, right? I mean, it may be chilly tonight, but it's not cold, right? Pressures on our marine resources, therefore, will change. Just more people, more pressures, more impacts on the watershed. And we also had a number of speakers over the last couple of years have talked about sea level rise and how that's really going to change the lagoon. And that has impacts far beyond some of the things that we think about. For example, in Dade County, one of the biggest concerns they have is saltwater intrusion into freshwater supplies. And that's a serious problem. Ironically, as we dispose of a lot of fresh water out to sea, as they say, other parts of Florida may be in short supply for water very soon. So our take-home message for tonight is the lagoon is a very dynamic estuary. It varies a lot in time and space. I hope you understand that. It's really important. It changes a lot. A lot of human impacts that have happened over the 100 years are still poorly understood. The management of the lagoon is challenging given this variability and the pressures from the surrounding watershed. We simply don't know enough about how the lagoon functions. That's what I want to know. I want to know, how does the lagoon work? There's a lot of work to be done. If I was a manager, thank goodness I'm not of the lagoon, but managers of the lagoon do require sustained focused scientific research and monitoring. I think we can contribute a lot to that, and I hope I've convinced you that we're trying to be a catalyst of these efforts and a leader of these efforts. But by all means, we're happy to work with all of the other institutions that are involved in the lagoon, because it's a big job. So I want to thank a lot of folks, Team Lobo and particularly some of the other folks that work with us, Brian for making that wonderful video on short notice, of course, and all of our funding. This is just part of it, I guess. And particularly our support from our Save Our Seas plate. So if you buy that Harbor Branch plate or any of the other ones, you contribute to our work tonight. So, questions?